Welcome, ladies and gentlemen. My name is Maximilian Wolf. The topic of this talk is the impact of generative adversarial networks on NetFlow-based traffic classification. The agenda for this presentation consists of the 5 main parts. Firstly, the motivation, objectives, and challenges of the following approach is given. Secondly, the foundations and the approach are discussed. Thirdly, the experimental setup is explained and the results are evaluated next. And finally, the experiments and the overall findings and takeaways are summarized. The domain of this work are network intrusion detection systems, which are commonly used to monitor network traffic for the detection of malware. The most simple approach is to separate normal and malicious traffic. There are several challenges included in this task, like the classification of the traffic itself, where the behavior of the normal users as well as their attacks change constantly. In order to create self-learning systems, large amounts of labeled and representative data are necessary, but they are rare. Given the encountered problems, the objective of this work is to improve network intrusion detection systems. This can be done by creating a self-learning system using neural networks, which are able to learn the classification by training. The shortcomings regarding the training data are approached by creating artificial training data, which are used to train the neural network. Based on the objectives, our approach uses 3 main ingredients. Firstly, the NetFlow file format only stores the metadata of a network connection, which uses significantly less resources, considers privacy concerns, and handles encrypted connections, in contrast to packet-based connection data. Secondly, since the network data are sequential information, where the sequence of connections can unveil attack-specific patterns, a model which is able to process sequential information is needed. Therefore, the used neural network is a long and short-term memory network. Thirdly, in order to create artificial but realistic training data, a generative adversarial network is used. Our approach uses the NetFlow file format, which only stores metadata of a network connection like time, the duration, and the used protocol. Based on these metadata, the behavior of network clients can be analyzed, which is used to detect attacks. The neural network requires a numeric encoding which preserves the semantics of the original data. Different types of data require different encoding approaches. For example, categorical data are one-hot encoded, while others are simply binarized like the field bytes. Since our training data are recorded within a few weeks, the date is excluded, since the information are less valuable in this case. Furthermore, the IP addresses have to be discarded, since the training and the test sets of our data uses the same IP addresses for the attackers. But our neural network should not learn to classify data based on the IP addresses, which would bias the model. We are using long and short-term memory networks. The LSTM block is able to process sequential information because it consists of a memory cell and multiple gates to modify and recall the stored information. Due to its memory, it is able to involve information of previously seen data into the decision process of currently seen data, which is beneficial to detect malicious behavior in sequential data like NetFlows. By stacking LSTM blocks on top of each other, deep architectures can be created, which are able to detect long-term dependencies in data sequences. The generative adversarial network itself consists of 2 neural networks which are set up in an adversarial competition. The generator creates fake data based on random input data. The discriminator tries to separate real and fake data. Based on the decision of the discriminator, the networks are updated to achieve their objectives. The generator wants to fool the discriminator, and the discriminator wants to detect all fake data. By iterating through a set of data multiple times, the generator will improve to create fake data which are as close to real data as possible. Due to this adversarial game, the generator is at some point able to create realistic, synthetic data without creating exact copies. The Wasserstein Generative Adversarial Network is an improved version of the original GAN, which is proven to work more stable. Later, the Wasserstein GAN was improved further, which resulted in a so-called vegan-GP in short. The original GAN uses feed-forward networks exclusively. This type of neural network is not designed to process sequential data. Therefore, our approach replaces them with LSTMs. Our setup consists of a baseline LSTM classifier and the LSTM vegan GP setup, where the discriminator is now called critic and is extended to separate the data based on the classes normal, anomaly, and fake. To guarantee comparability, the classifier and the critic share the same network architecture and are trained and tested with the same data. Our experimental setup is tested on two datasets: the CISIS6, which has a consistent network architecture but only a few attacks, and the CISIS6 botnet dataset, which features a large diversity of botnet attacks but no consistent network architecture, since it is a composition of multiple individual datasets with different network architectures. Based on the standard classification evaluation matrix, the LSTM classifier and the LSTM vegan GP achieve acceptable results for CISIS6, but not for the CISIS6 botnet dataset. This may be explained by the structure of the datasets. CISIS6 contains equal attack types with equal behavior in the training and the test set. The CISIS6 botnet dataset contains novel botnets and therefore novel behavior in the test set. Maybe the network architecture used in the experiments could not generalize well enough to detect novel attacks, or the training subset of the CISIS6 botnet dataset is not representative enough to allow generalization of the models. Another reason could be the integrity of the datasets. CISIS6 has a high integrity because it is recorded in one consistent network architecture with consistent behavior of normal users. The CISIS6 botnet dataset is a mixture of multiple datasets that are synthetically combined, which increases the diversity of the attacks but demolishes the network infrastructure in terms of integrity and consistency. In short, the models demonstrate high precision scores but low recall scores. The LSTM vegan GP models achieve a higher accuracy and F1 score on both datasets. The false positive rate is the most important metric and demonstrates very low scores on both models and datasets. By additionally taking the application-specific metric of detected attacks into account, an improvement can certainly be detected. In the CISIS6 dataset, all models could discover all types of attacks. The LSTM vegan GP increased the number of botnet detection on the CISIS6 botnet dataset and retained a low false positive rate. Our work presented you the effects of artificial data enhancement on two different datasets. The experiments show that the data augmentation increases the classification performance while a low false positive rate is preserved. Thank you very much for watching this presentation.